again. Yeah, it's morning for me. Not sure what time of day it is for you. This is part two of CSEC thermophysics. We left off at thermometers, and we have to continue from phases of matter. Let me double T E R. Good. There are three phases of matter. I know you're going to say that there are four, but for the syllabus, we just consider the three simplest forms of matter: solid, liquid, and of course, gas. No, in a solid, atoms are very closely packed. These atoms are in a regular repeating pattern. In a gas, the atoms are fairly widely spaced. And there is no pattern, no arrangement. The molecules of gas are everywhere. Well, would you look at that? I skipped liquid. I actually meant to say liquid, my bad. Like ID, sorry, liquid. In a gas, the molecules are spaced out much more than in a liquid. Now, what are the key differences between these three phases of matter? Well, the difference between the phases comes down to two things: molecular spacing. Molecular spacing, intermolecular forces and spacing. For a solid, the forces are very strong, and they're not spaced, but rather closely packed. For a liquid, the forces are weak, and they're not closely packed. For a gas, the forces, intermolecular forces, are very, very weak. And the molecules are very widely spaced. You know what? Let me write that Y over. Yep. Widely, SPACED. And these are your three phases of matter. Solid, very strong. Yeah, I should put the word very here. Very strong forces. And I should put a very there as well. Very closely packed. In a liquid, these forces are much weaker, and they're not as closely packed as in a solid. And in a gas, well, very, very weak and very widely spaced. So, excuse me, I don't have my recording voice on as yet. We move to gas laws. Now, there are technically just three gas laws. Gas laws. There are three gas laws, and the first gas law is Boyle's law. BOYLE apostrophe S, Boyle's law. And Boyle states for a fixed mass of gas at constant temperature, pressure is inversely proportional to volume. This is Boyle's law. For a fixed mass of gas at constant temperature, pressure is inversely proportional to volume. That means if we increase volume, we decrease pressure. And if we decrease volume, I should probably put that on the other side. If we decrease volume, we increase pressure. This is Boyle's law. If we were to plot a graph for Boyle's law, we would have 1 upon V on this axis, P on that axis, and the graph should be a straight line through the origin. Now Boyle's law has an equation, right? This expression leads to an equation. The equation is PV is equal to a constant. And we also have what we call initial and final conditions. The initial conditions are before a change, and they're represented by subscript 1. The final conditions are after a change and are represented by subscript 2. Anyways, back to my little graph. Graph should be straight line through the origin. And this is the equation that is usually applied to Boyle's law. Next comes, one second. Charles, Charles, Charles' law. Now, Charles said, for a fixed mass of gas, at constant pressure, volume is directly proportional to temperature. For a fixed mass of gas at constant pressure, volume is directly proportional to temperature. Now again, if we increase temperature, we increase volume, and if we decrease temperature, we decrease volume. Charles' law is very important because it gives us the foundation, the basis, the framework for defining the Kelvin, or creating rather the Kelvin scale. Charles got a graph which he extrapolated. If you're doing maths, you probably should know what that means. And he extended the graph all the way to the point where the graph cut the x-axis. One second. Excuse me. Now, where was I? Yeah. Charles found this point. By the way, I didn't even label my axes. Yeah. Charles found this point, and he called it absolute ABSOLUTE, absolute zero. Now, absolute zero is minus 273. I put 27K, sorry, 273 Kelvin. Now, you might minus 273 Kelvin. Anyways, we'll come to that just now. Actually, what did I say? I'm sorry, I'm sleepy. I woke up like 15 minutes ago and I'm recording this. Minus 273 degrees Celsius. Anyways, yeah, forgive me for that. Now, the label he called this, well, the label he gave to this was 0 Kelvin, Kelvin. It's written like 0K, but you know, if I didn't say it was 0 Kelvin, it would look like okay. Yep, so that's why I wrote the word 0 and Kelvin. And this is the lower fixed point on the the Kelvin scale of temperature. The upper fixed point is the triple point of water, right? And that is somewhere here. Triple TRIPLE point of good old H2O. And these are the two fixed points on the Kelvin scale of temperature. Absolute zero, or some people say absolute O, and the triple point of water. Now the triple point of water, some textbooks use 0.15 degrees Celsius, some use 0.16, some just flat put 0.1. You might see some different things, but according to the syllabus, let me just check to see what the formula is on the syllabus. I flew right past it. They just use 273. Then we might just, let me check that again, because I do not want to be wrong. Expansion, blah blah blah. Yeah, they just have 273. Alright, well, for the sake of argument, this is how it should be, but anyways, you know what? I shall just put that back and leave it as it was. Anyways, the syllabus has 273. I'll explain. There's a reason that can work, or why we can use it as well. Now, what Charles said, back to this, hopefully I haven't lost you, is that this is your 0 Kelvin. Yeah, that's your 0 Kelvin, right? Your 0 Kelvin. And this is, well, this is 273 Kelvin. In other words, if you're looking at the size of the unit, 1 Kelvin is the same as 1 degree C, right? In terms of size. It's just that he chose different points. Now this makes me realize that I did not explain the Celsius scale when I was supposed to, but this is a perfect time to do it. Now the Celsius scale is based on 2 fixed points as well. So let me quickly explain that. The CELSIUS scale of temperature. Now the Celsius scale is based on 2 fixed points, 0 degrees Celsius and 100 degrees Celsius. By definition, this point is the melting point of ice. And this, I should remove that arrow, and this is the boiling point of water. These are the 2 fixed points on the Celsius scale. Now the problem is based on where you are in the world in terms of elevation, and also, yeah, basically where you are in the world. Let's just make it simple. These two will differ. Also, things like impurities in water may affect the melting point of ice and even the boiling point of water. Adding salt to ice causes it to melt at much lower temperatures. Anyways, that's a different story for another day. And this between 0 and 100 is 100 units. 100 units of temperature. What Charles did was he decided not to make a different unit in terms of size. So when he got his minus 273, he just decided that minus 273 would be 0, and the upper fixed point, which he took, which he took as the triple point of water, was 273. Now, CSEC wants you to not use 0.15 and just use 0, so we will oblige them and use 0. There's a formula that relates temperature in Kelvin to temperature in Celsius. Now, temperature in Kelvin is equal to temperature in degrees Celsius plus 273. This is the formula that relates the Kelvin scale to the Celsius scale. We do not use Fahrenheit because Fahrenheit is American, not insulting American things, but it's based on the Celsius scale. Anyways, this is all related to Charles' law. So let me get back to this. Again, just to recap, that's a lot of information you just got. Charles said this. Charles said that volume depends on temperature. Now, just like we did with Boyle's law, if we have our equation, and our equation states that volume is proportional to temperature, we could say that volume over temperature is some constant, and that V1 over T1, initial conditions, equal to V2 over T2, final conditions. Again, this is before some change, and this is after. The final gas law is the pressure law, the Pressure, the pressure law. Now, the pressure law states that for a fixed mass of gas at constant volume, well, would you look at that? I lost my whiteboard. Wow. I have it back. Ain't that some stuff? Anyways, it says for a fixed mass of gas at constant volume, the pressure is directly proportional to the temperature. And again, you should know the drill. If we increase temperature, we increase pressure. And if we decrease temperature, we decrease pressure. Now this law should give you, well, an equation that says P over T is a constant, and P1 over T1 is equal to P2 over, I nearly put V2, but it is T2. Anyways, this is the good old pressure law. Now the graph for the pressure law is going to resemble the graph for the it's going to resemble the graph for Charles' law. And it is not going to go through the origin it's going to have a shape something like this. And again, depending on your apparatus, should I say again? Yeah, depending on your apparatus, if you're carrying this experiment out in school, you might not be able to approach or even reach zero. But if you're in a like fancy industrial lab, yeah, you should be able to push the graph back. So this is the pressure law, and oh, I didn't label my axes, P and T. Yeah, these are your gas laws, and that's my 20 minutes. I guess I hopefully remember not to record when I'm too sleepy again. Anyways, take care, stay sane, stay safe, and I will see you in the next video. Bye bye.